Hello everyone, thank you for joining me today. In this video presentation, I'll go over the research work titled Importance of Smoothness Induced by Optimizers in Federated Learning for ASR. I want to start by thanking my collaborators Tatiana, Martin and Honza, without whom this research would not be possible. We start by going over the basics of federated learning. We begin by initializing a model at the server. Once we have the central model, we broadcast them to devices where the data resides. Each device then does local training on their private dataset. After this, the devices send the model updates back to the server at the end of a training period. The server then aggregates these updates using uniform averaging or weighted averaging. The aggregated update is then applied to the central model, which is sent back to the devices, and this process is repeated. This is the most basic version of the federated learning algorithm. However, researchers have found out that we can actually benefit from training on devices for several training rounds. In this particular work, we consider this particular algorithm for the rest of the experiments. At this point, we now turn to federated learning for ASR. Specifically, we want to look at what are the benefits of federated learning. The ones that I wish to highlight include the reduced dependency on data collection. It also reduces the computation and storage needs. Federated learning can also be explored together with differential privacy, which further helps reduce data leakage and enhances the user privacy. However, ASR benchmarks are largely overlooked in federated learning research. There are several prior works which are unable to even achieve convergence when training with federated learning. We can look at some of our main contributions now. Firstly, we summarize the applicability of prior work in federated learning towards ASR. We find it is non-trivial and the direct application will mostly not converge, let alone lead to any state-of-the-art models. We recognize these gaps and we propose several methodologies that can help reduce the performance gap between federated learning and the centralized model training. During this effort, we also observed a significant impact of the adaptive optimizers, which leads us to our third contribution, where we analyze why exactly do these optimizers improve over the vanilla SGD optimization. Next, before I jump into the results, I would like to go over some experimental setup briefly. First, dataset. We use LibreSpeech open source dataset, mostly because it has associated speaker ID. Also, it has a considerable difference in terms of quantity and quality of data that is available per speaker. We'll come back to this particular aspect of speaker diversity in a later slide. In terms of model, we run our experiments using the open source VNet model. This choice has two reasons. First of all, this model is open source, which makes it easier to reproduce our results. Secondly, it is a practical ASR model, which is quite close to production deployed models at several settings. Apart from federated learning, we consider centralized training for comparison. These models are trained for about 80,000 updates or until convergence, whichever comes first. We use warm-up scheduler to push its performance. In terms of federated learning, we simulate the setting using LibreSpeech metadata on speaker ID. Basically, each device is simulated by considering data from one speaker only, without any overlap of data among devices. We train the federated learning model for 2000 centralized aggregation rounds, which is a practical number of aggregation rounds even in real-world settings. Each model is trained for 10 local epochs during each federated learning round, and we consider 16 devices in federated learning for most experiments. Some of the experiments have different settings, but I will point out to them as we go through the slides that follow. There are more details for replicating the results. I invite you to take a look at the paper to get the exact details. At this point, let me also differentiate between two federated learning training schemes that we use, training from scratch and training with seed model. For training from scratch setting, we present experiments where the federated learning system is trained using all the 960 hours in the LibreSpeech dataset. While for training from a seed model, we split the data into two sets. Here, the smaller 100-hour data is used for central training, and the remaining 860 hours of data is used for federated training. At this point, I would also like to point out that there are no overlaps among any of the training and evaluation sets, both in terms of speaker and actual utterances. We can now move on to some results. Let's begin by going over some baselines. The first baseline is a centrally trained conformer model similar to the one considered in our federated learning experiments. The second one is the current state of the art in federated learning using LibreSpeech dataset. This particular work uses RNN model with a transducer loss. Finally, we also consider another federated learning work which uses a similar conformer model. This particular work points out that they find it impossible to achieve convergence when training from scratch. In terms of applicability of prior work in federated learning, we start by evaluating the vanilla federated averaging. We find that the direct application of this algorithm gets stuck in the local minima. However, by applying simple tricks such as warm-up, we can improve the performance significantly. We can further improve the performance if we start the training with a seed model. We next consider training using adaptive optimizers in federated learning. When we use Adam as a central optimizer, we observe that it fails to converge. However, we can use simple trick called optimizer switch to achieve convergence. In this trick, we start by training with SGD as the central optimizer and switch to Adam after a few rounds of central aggregation. However, this performance seems quite similar to the vanilla federated averaging, which is quite odd. However, if we were to consider training with seed start, Adam starts performing much better than SGD, especially on the noisy dataset. Until now, all the plots we observed use SGD as the local optimizer. We next check what happens if we switch it. In particular, we find that when compared to SGD as local optimizer, LAM improves the performance significantly, which can be improved even further if we increase the number of devices in the federated learning setup. Observing the benefit of changing the local optimizer, we also look at the effect of changing the central optimizer. If we change Adam to Adam W, while we observe there is only a minimal benefit, we have already beaten the state of the art that existed in federated learning on the LibreSpeech dataset. While these differences are minimal, if we switch to training from scratch, we can observe a greater difference between the choice of central optimizer, specifically if we look at the last two bars in these plots. At this point, a question arises as to why do we observe these differences in terms of adaptive optimizers when compared to SGD. So let's go over the intuition why adaptive optimizers work, if they work at all. So the main intuition behind this is that adaptive optimizers engage in scaling of the learning rate along multiple coordinates almost independently by using the second order statistics. This leads us to believe that internally these optimizers are suppressing the heterogeneous components which do not conform with the aggregated statistics that are aggregated during the training. We in fact observe that different optimizers can do this to different extent. For example, if we look at this plot where we show the cosine similarity between different aggregated models, here the top row shows the aggregated raw updates that are collected as pseudo gradients, and the bottom row shows the effect of the optimizers, which are Yogi and Adam. We can see that the interaggregation round similarity is more for Yogi than compared to Adam. This sort of effect shows us that the available variation in the heterogeneous directions are less in case of Yogi when compared to Adam. Intuitively, this means that there is a reduction in the effect of heterogeneity among the updates at different steps. Similarly, we can also analyze the effect of LAMB as a local optimizer. We again plot the cosine similarity of client updates at a single aggregation round, and we can see that the mean similarity is higher for LAMB. I think this is resulting from the layer-wise adaptive nature of the LAMB optimizer. This layer-wise adaptive nature ensures that the effect of heterogeneity in the deeper layers is minimized. This brings us to the end of this presentation. So, in summary, we wish to highlight that ASR benchmarks are overlooked in federated learning research but are not trivial. We provide with several recipes that can help us achieve state-of-the-art numbers in federated learning using LibreSpeech dataset. And we finally give intuitions into why adaptive optimizers work at all and what is the effect of these optimizers in terms of inducing smoothness over the gradient updates. I invite you to refer to our paper for more details, and feel free to contact us directly if you have any questions. Thank you for your attention and have a great day.